Hello, this is Questionable Coding with Vladimir, and today we're going to talk about a data structure called heap. It's quite interesting. It's like an intersection between an array and a tree. And we're going to cover multiple things about a heap, just general description. Binary heaps is it's the most famous and useful form of a heap. And also we're going to cover main operations with a heap and their complexity. And also we'll implement the binary heap in JavaScript, because JavaScript doesn't have built-in heap implementation, so we have to do it ourselves. But let's start from the very beginning. First of all, heap in general, not a specific heap, not a binary heap, it's a tree-based, partially ordered data structure. Currently on the picture you see a binary tree, but for heap in general there can be multiple children, more than 2. But we won't use heap right away. We are going to work with binary heap, but still, let's just agree that there are two main types of a heap. It's max-heap and min-heap. And there is not a big difference. Max-heap will efficiently give you the biggest element in our set, and min-heap will give the smallest. And if you understand one and you know how to implement one, you automatically know how to implement another one with small changes. And there is a rule that any node key, it's for max-heap, but you can inverse it to apply it for a min-heap. So any node's key, for example, let's say we take 44, so the key is 44, is less than or equal than the parent's key, so key 90, and more, it's bigger or equal comparing to child's key, so we have 40 and 25. So this happens on every node, of course, and the thing here is we don't distinct left and right child. So for example, in this case, the biggest element is to the left and smaller to the right, 25 and 40 to the left. And near it, it's an inverse situation where 5 to the left and 69 to the right. Okay, well, let's move on. Now let's talk about a binary heap. So first of all, it's a complete binary tree. What do I mean by that? So a complete binary tree is a tree that is filled from top to bottom, from left to right, except the last row. So for example, if we would have only 44 and 70 nodes and we add children, we need to add them from left to right. First the left child of 44, then the right child of 44, and then a left child of 70, and the next element will go as a right child of 70, and then the new row will begin. So that's how we fill it. And also below there is an array implementation of that heap. So you see the element on the top, it's in the beginning of the array. Then we just go row by row and we see 44, 70, and so on. So in general we can replace any binary tree by such an array. But the problem is that if it's not complete or full, then we have a problem with empty spaces. And some binary trees, they can be very not balanced. So we can have a tree that has only left childs for every node or right childs, and it will be very large. So I mean the depth of the tree will be big, it will equal to n, so n elements, and we'll have to fill in every gap, but instead of a value we'll use null, for example, to just signify that there is no node, but we expect it to be there because we need an array representation of that. In that case, it will be extremely inefficient. We'll have a huge array for 10 elements. We'll have 2 in power of 10s, so it's over 1000 elements in the array. for almost nothing, for 10 elements. But for a complete binary tree, it's not a problem because everything is filled in, there are no gaps here. Okay, let's move on. What are the common operations for the heap? The first operation is called pull. It can also be called other ways like extract, but the main thing is that we want to extract the maximum element. Right now we're working with max-heap, but for min-heap you just think that you extracted the minimum element. So how do we do this? There is an animation, it will happen right now, and it will do the same thing, but in array and in tree simultaneously. So don't be surprised. So first of all, we pop the top element and we use it. So it's usually the purpose of our data structure to get such elements, maximum elements. Okay, so we removed it and we returned it to some client code. And then we're moving the last element to the top. And we shrink an array. I didn't show it here, but the array becomes one element smaller, so there are no gaps. And then we heapify down, which means we recursively compare our element to children, and we swap it with the bigger child. So right now we compared 5 with its children, 44 and 70, and we swap them. We would do it recursively for the new position of 5, but there are no children for 5, so it's the end of our heapify process. Another important thing, the second one, it's push or insert of the element. So we have a heap, max heap, and we need to insert something, and we should keep the heap property. So first of all, we insert element to the end. So our array becomes bigger, and we insert 99. And then we heapify up. We recursively compare this new element to a parent, and if our element is bigger, then we swap it with a parent. We swapped it, and then we repeat the process for the new position, and we also swap it. So it bubbled up to the very top. And now we have a proper heap once again. Okay, now we're going to talk about array and indexes. How can we find one element having an index of, for example, a new element that we just added? We need to find its parent or its children if we go from top to bottom. So to the left you see a heap, a proper binary heap, and to the right you see the same thing, but I show only indexes, how we can calculate them. So we're working with element with the key 44, and it's I, like index, on the picture to the right. And if we want to find a left child, then we need to multiply this I by 2 and add 1. And if we want to find the right child, we'll do it, but do the same, but we'll add 2. So at the bottom you see an array that is represented to the left, the same tree but in the form of array, and we have indexes from 0 to 4, and we can calculate that. For example, for 44, if we want to find index of its right child, we take 1, we multiply it by 2 as written in formula, and it becomes 2, and we add 2. So the item to the right will be 40. It will have index 4 and it will be 40, as you may see in the tree. The tricky part is to find the index of the parent. So the problem is that if we want to find an index of a parent, we also need to calculate it, but there are maybe two elements that have the same parent. So the formula should handle that, and that's why we use mass floor. So what we do, we subtract 1 from our index I, and we divide it by 2. Okay, let's move on. what are the common operations of a binary heap? So standard are push, pick, and pull. So push, it's insertion of a new element. Pick, we just return the top element. It's very easy. It doesn't alter the heap itself. And pull will return the element and remove it. And we already looked through push and pull on the slides before. And there are some optional methods. Is empty if you want to check if the heap is empty. The size if we want to track the size and return it. And merge if we want to merge two heaps, but it's out of our scope. So what's the complexity of a heap? So if we want to insert an element, we will use log n. So we have a tree, a binary tree, we compare it, it will be log n, and I think it's not a question for you. If we want to pull something, so to extract and re-heapify, we'll also use log n, because we'll return the last element, we'll move it to top, and then we will go through the entire tree in the worst case. And it will also require log n complexity or steps. And yeah, search will be a big O of n, because we can't search in this. We need to go through every element and compare it. And pick will cost us nothing, because we won't change the heap. We won't need to re-heapify it, and that's why we just return the first element and its constant time. So right now we're going to implement a max heap / priority queue, thinking that the maximum key is the maximum priority in the queue. But let's deal just with the max queue without mentioning the priorities. So this we need to construct the heap at first, an empty heap. So we want to use an empty array to store all the values, and it will be the only thing we'll set up in the constructor. What else? We need helper methods to get an index of a parent of a current element and its left and right child. So let's create a method called getParentsIndex. GetParentIndex. And we'll pass our index here. And we'll return, as we discussed, mass floor I minus 1 divided by 2. We need to get left child's index. Get left child index. And we'll return, it's a bit easier, we'll return I multiplied by 2 plus 1. And almost the same for right child index. But we need to increment it even more, so it will be I multiplied by 2 plus 2. Okay, so we have 3 helper methods, and it's enough for us to do all the elements like heapify and do swap, which will take 2 indexes, index 1 and index 2, and we'll swap elements that are there for these indexes. We're going to use a temp variable here just to make it easier and maybe more readable. So temp this data index 1, and then we will write this index, and it will equal the key that is on index 2. And the inverse thing will rewrite index 2 value. It will be our temp value. Okay, so we have everything that we need in place. What we're going to do next, we're going to implement push method. So push method will add one element to our heap, and it's also pretty straightforward except one function. So first of all, we need to add this element to the very end of our array. That's quite easy. We just do this data length to find the first unused index, and it will be just key. And then this key may be the biggest key in our heap, so we need to follow our heap requirements and we need to change the heap. That's why we're calling heapify up. It's not yet implemented, we're gonna implement it right away. Okay, so heapify up doesn't accept any argument because it always deals with the last element in the array. So let's say our current index is the last one we added. It will be this data length -1 because it's not zero based and indexes are zero based. Now we need to follow a while loop. So until our element is bigger than its parent, we need to swap them and follow this logic recursively. So let's try to compare them. Oh, I made a mistake here. This. So we have this data current index. I think we need to call it current index just to make it more clear. More than this data get parents index for current index. So while it's happening, we need to swap them. To do this, we just call the swap function, and we pass our current index as the first index, and we pass its parent index. And we need to reassign our current index because we need to repeat it for a new position of our key that we try to bubble up. So we say that current index will equal this get parents parents index, sorry. Okay, that seems good. I think it should work and we need to test it. I prepared a very straightforward code for that. So I create a new heap here. I output it, but it doesn't matter right now. I think it's okay. I push values that we had in our presentation, hoping to get something similar that we had on the images. So then I'm joining that with a comma, and we'll use this string in LeetCode because they have a nice visualization of trees. I prefer to use it if I need to do something quick. So first of all, I'll launch this code. And it gave me some values. They already look pretty nice. So I'm going to LeetCode. Yeah, the visibility is not the greatest, but I think you see it. So we have 5, 40, 70 as a parent, and it's good, and 90 on top, which is also good. To the right, we have 25 and 44. Looks okay to me. It's definitely a heap. I think we did this part in the proper way. Now we're going to return to our code and implement a poll. So it's very important. We not only push to our heap, but we poll from it, and we expect the biggest element from max-heap. So first of all, I think it's the hardest function here. So first of all, what we do, we need to keep our value. So let's say const, I would say max value will equal this data, and we'll pick the 0 element. It's on top. Then what we do, we remove it or we replace it by the last element of our array. So this data 0 equals to this data length -1. Okay, now we reduce the length of our array, so we remove the last element that we just assigned to very top. What we do is this data length -. We decrement it and it should just remove the last element. So our array became smaller. And we have two things left. First of all, we need to make sure that our heap is still a heap, so we need to reheapify it, and we'll call heapify, but not up but down, because we need to start from the top and go to the bottom, because we took an element from the very end and put it in the very beginning. And then we'll just return the max value. Okay, now we're going to implement heapify down function, which is the hardest function here. And what we're going to do, we're going to work with the top element. So we also need our current index, which by default will be just 0. And then we're going to write a while loop to have a recursive call. So what we're going to do in while? So we take our current element, it will be on top, and we compare it to its children. If one of the children is bigger, then we just swap values of our current value and our children value. Because if our element is smaller, then it needs to be lower than its children, bigger children. And that's how we're gonna bubble it down to the place where it belongs. So for that, we'll just check if we have a left element. Until we have it, we will proceed comparing. So this data, and we have left child, and if it's not undefined, then we continue. If we don't have a left child, we definitely don't have the right child, because we have a complete tree. So we need to find the biggest children right now. We want to use let biggest child index, and we'll just assign it to the left child for now. Then we'll check the right child. So if there is a right child, I'll just copy this part here. And the right child is bigger than our left child. And we can also copy this part. Forgot and it's bigger than the left one. We are going to assign a new biggest child index. Something, yeah. So our biggest child index will be equal to the right index. That's how we found the biggest child of 2. It sounds looks a bit complex, but it's really not. So now we're going to compare our current element with the value for this biggest child index. If our current value is less than this data biggest child index, then we need to swap them. This swap, and we call in with current index and with biggest child index. And we need to do it the same logic for the new position of the current index. So we need to assign it to the index of the biggest children. So once again, we swap the top element with one of its children, the biggest children, and we want to check the same thing for its new position. And now the children is on top, by the way. Okay, else we have everything right and we just return from the while loop. That should be it. And let's check it. So I have a code. We first push the values, then we poll the values. And I collect all these polled values in an array, which should be like a decreasing array from the biggest element to the smallest. Top 5 items. Let's execute the code. Yeah, and we have it. So top 5 items, 90, 70, 44, 40, 25, if you see it. So everything is working good. And that's how we implemented our max-heap. It's a bit complex. It's very useful to know it, to learn at least how it works, maybe to implement it a couple of times. And it can be a very useful data structure for implementing a priority queue, for finding case, max, or min element. There are a lot of tasks like that on lead code, and you can face something during interviews. And I think that's it. I hope it was helpful, and we'll have plenty of videos in the future for other data structures. Please check what's already there, like trees and others. Yeah, there are a lot of them. So stay tuned and subscribe.